Have you ever looked at the tiny chip inside your phone and wondered how something smaller than your fingernail can hold more computing power than the computers that sent humans to the moon? It sounds impossible, but it's true. That tiny black square controls everything from your text messages and photos to artificial intelligence, satellites, and even modern hospitals. Inside it are billions of microscopic switches working together every single second. They are so unbelievably small that if one were enlarged to the width of a human hair, the hair would become wider than a football stadium. Building something this tiny isn't just difficult, it's one of the greatest engineering achievements in human history. What's even crazier is that every advanced microchip begins as ordinary sand. The same material you walk across at the beach eventually becomes the brain of your smartphone, laptop, gaming console, electric car, and countless other devices. But transforming a grain of sand into the world's most advanced technology requires billions of dollars, factories cleaner than hospital operating rooms, machines worth more than luxury mansions, and manufacturing so precise that even a single speck of dust can destroy weeks of work. Today, we're taking you inside one of the most incredible manufacturing processes ever invented. You'll see how engineers turn simple silicon into processors containing over 100 billion transistors, each smaller than a virus. By the end of this video, you'll never look at your phone or computer the same way again. The story begins in 1947 at Bell Laboratories in the United States. Three scientists, John Bardeen, Walter Brattain, and William Shockley, invented the transistor, one of the most important inventions in history. The original transistor was roughly the size of a thumb and replaced bulky vacuum tubes that powered early electronics. That single invention completely changed the future of computing. Fast forward to today, and the difference is almost impossible to believe. Modern processors can contain well over 100 billion transistors packed onto a chip that easily fits on your fingertip. Many of the world's most advanced chips are manufactured using a 3-nanometer process. To understand just how tiny that is, consider this: a human hair is about 70,000 nanometers wide. That means these microscopic structures are roughly 23,000 times thinner than a single strand of your hair. Creating features this small pushes science to its absolute limits. Only a handful of factories anywhere in the world have the technology to manufacture chips at this scale. These facilities are known as semiconductor fabrication plants, or simply fabs. They aren't ordinary factories, they're among the most expensive buildings humanity has ever constructed. Some modern fabs cost more than $20 billion to build. Inside them are machines so valuable that a single one can cost over $150 million. Transporting these machines is an enormous challenge because they are made from more than 100,000 precision components and often require multiple cargo aircraft and specialized trucks just to reach their destination. Every piece must arrive in perfect condition because even the slightest vibration or contamination can affect performance. But before any of those incredible machines can begin their work, manufacturers need the most important ingredient of all, silicon. Although silicon is one of the most common elements on Earth, not every source is suitable for making computer chips. Manufacturers need exceptionally pure silicon dioxide, also known as high-quality quartz. Some of the richest deposits are found in countries like Australia and Brazil, along with locations such as North Carolina in the United States. The journey starts by heating quartz together with carbon inside giant industrial furnaces at temperatures exceeding 2,000 degrees Celsius. At this extreme heat, oxygen separates from the silicon dioxide, leaving behind raw silicon. It sounds impressive, but this material is still only about 98% pure. For everyday industrial applications, 98% purity would be remarkable. For microchips, however, it's nowhere near good enough. Modern processors demand one of the purest materials humans have ever created. To achieve this incredible level of purity, manufacturers use an advanced purification process known as the Siemens process. During this stage, the silicon is converted into a gas before being transformed back into solid form. Instead of forming randomly, silicon atoms are deposited one by one onto carefully prepared rods, slowly building extremely pure polysilicon. The result is astonishing. The finished material reaches a purity of approximately 99.9999999%, often called 9 nines purity. Put another way, unwanted impurities are measured in just a few parts per billion. This level of purity is even greater than that of the finest investment-grade gold. Producing material this clean is one of the greatest achievements in modern chemistry and materials science. Engineers now begin one of the most remarkable steps in chip manufacturing, growing a perfect silicon crystal. Ultra-pure silicon is melted at about 1400 degrees Celsius inside a quartz crucible. A tiny seed crystal is lowered into the molten silicon and slowly rotated while being pulled upward. As it rises, silicon atoms naturally align with the seed, forming one enormous, perfectly ordered crystal. This process, called the Czochralski method, takes many hours and requires precise control of temperature, rotation, and pulling speed. Even the slightest mistake can ruin the entire crystal. The finished product is a massive silicon ingot, nearly 300 millimeters wide and weighing over 200 kilograms. It is then sliced into hundreds of thin wafers using diamond-coated wire saws. Each wafer is about as thick as a credit card, but its surface is still covered with microscopic scratches. To remove every imperfection, the wafers undergo chemical-mechanical polishing, or CMP. This creates an atomically smooth, mirror-like surface. If one of these wafers were enlarged to the size of a football field, its tallest bump would be only about half a millimeter high. That level of precision is essential because billions of transistors will eventually be built on top of it. The polished wafer is then transported into an ultra-clean semiconductor fab. The air inside is about 10,000 times cleaner than a hospital operating room, because even a single dust particle can destroy thousands of tiny circuits. Stored inside sealed FOUP containers, the wafers begin a 3-month journey through more than 1,000 manufacturing steps. First, a thin insulating layer of silicon dioxide is grown on the surface. Then, a light-sensitive chemical called photoresist is evenly spun onto the wafer, preparing it for the incredible process of printing billions of microscopic circuits. Now comes the most important step in chip manufacturing, photolithography. At the heart of it is the world's most advanced machine, the Extreme Ultraviolet Lithography, or UV, system, built by ASML. Each machine costs over $150 million, weighs more than 100 tons, and contains over 100,000 precision components. Inside, a powerful laser fires 50,000 times every second at microscopic droplets of molten tin. The impact creates plasma reaching nearly 500,000 degrees Celsius, producing extreme ultraviolet light with a wavelength of just 13.5 nanometers. This light is used to print features only 3 nanometers wide. Because UV light is absorbed by air, the entire system operates inside a near-perfect vacuum. Instead of lenses, it uses incredibly precise mirrors. If one were scaled to the size of Germany, its largest flaw would be just 1 millimeter high. The light passes through a circuit mask and projects the design onto the wafer coated with photoresist. After chemical development, plasma etching removes exposed material, carving microscopic patterns directly into the silicon. This entire cycle coat, expose, develop, and etch, is repeated dozens of times, building over 100 perfectly aligned layers. Next comes ion implantation, where atoms like boron and phosphorus are fired into the silicon. These atoms change its electrical properties, creating the billions of transistors that act as tiny on and off switches. Finally, ultra-thin copper wiring is added layer by layer, connecting every transistor into one massive network. After nearly 3 months and more than 1,000 manufacturing steps, the wafer finally contains hundreds of finished chips. But there's one problem. Not every chip works. Even a microscopic defect can ruin an entire processor. That's why every chip must now be tested before it can power the devices we use every day.